Hi, welcome to videos on RC network. So in this video we'll see how does the RC network's behavior with respect to time. So let us first consider a capacitor having a capacitance of C, and let us consider a switch, and then let us have a resistor by value R that is connected to this switch. So let us consider this switch as S, and let us assume that this switch is initially open, and let us try to close this switch at t uh, equal to 0. So let us assume that this capacitor has got a initial voltage V0 that is being stored in this parallel plate capacitor. So we are looking at what is the behavior of this capacitor voltage. So I'm looking at what is Vc of t. So with respect to time, what happens to this capacitor voltage whenever this switch is closed at t is equal to 0. So of course we know that since there is a resistor, whatever charge that is stored in this capacitor, which is resulting in an initial capacitor voltage of V0, has to start discharge through this resistor R, and it has to dissipate across resistor R. So let us try to understand what is the expression for this capacitor voltage when this switch is closed. So, so let us write the equivalent circuit of this RC network when this switch is closed. When the switch is closed, it will certainly look like something like this. So here this is the equivalent circuit, or the circuit that how it looks like whenever that switch is closed. So you have a capacitor voltage, initial voltage, that is V0, and let us consider a current of IR flowing through this resistor, and there is a current of IC flowing through this capacitor. So if you consider this as node A, so if you write KCL at node A, so node A, we know that okay, both the currents are leaving, so we end up with IC plus IR is equal to 0. So both the currents are leaving and no currents are entering to node A, so IC plus IR is equal to 0. If you try to find out what is the expression for IC, which is nothing but C into dV by dt, and if you try to know what is IR, it is the voltage that is there over here, which is now V0 V0 by R, V0 by R. So this is the expression for IR. Of course, if you want to write it, suppose if you consider this voltage in general as V, so you can simply write it as V by R. So let us consider this as simply V, which is the voltage across the capacitor. Of course, V0 is the voltage that is across the capacitor when it is when it is open, that is initial voltage. So let us consider the current flowing through this is due to the voltage that is there across this capacitor at any point of time. So let us take it as V as the voltage, and V by R happens to be the current flowing through that resistor R. So let us try to substitute that. Now this is equal to C into dV by dt plus V by R is equal to 0. So let us just try to solve that particular expression. So we have this dV by dt plus V by R is equal to 0. You divide entire thing by C, so I will end up with dV by dt is equal, plus V by RC is equal to 0, which you can further of course you can make a slight arrangement, or you just simply multiply it by dt. You will end up with dv plus v into dt by rc. So this is equal to 0. So now you try to take this v onto this denominator, then this becomes, that is divide it by v. So you will end up with dv by v plus dt by rc is equal to 0, which you can ultimately write it as dv by v is equal to minus of dt by rc. So this is the expression what you end up with upon doing some alterations. Now you integrate it over the entire period. So when I say integration, now you are integrating this from voltage, initial voltage V0 to Vt of t, and this integration you can start from t is equal to 0 to, you can take it up to infinity, so now of course we can write it as, of course this is 0 to, let us take it as a finite time t instead of taking up to infinity. So it is 0 to t. Suppose we know that the integration of this happens to be ln of v with limits v0 and v of t, and this happens to be minus of t by rc with the limit as 0 to t. So we can rewrite by applying the limits, we can write it as ln of the then minus of ln of v naught, and then this is equal to minus of t by rc plus 0. Now we are simply applying the limits. So this happens to be this, I can further rewrite it as ln of v of t by v naught. Of course v naught is the voltage across the capacitor at before that switch is closed. The initial voltage across the capacitor is equal to minus of t by rc. Now you take the exponential on either side, then this reduces to vt by v naught is equal to e power minus t by rc. So that now you can further write it as, now this vt is nothing but, so vt is, you can see it's exactly coming as, vt is nothing but the voltage across the capacitor at any point of time, that is v of t is given by v naught into e power minus t by rc. So this is the expression for the capacitor voltage at any point with the initial voltage across the capacitor as V0 and R as the resistor to which this capacitor is connected, and C is the value of the capacitance. So if I have a capacitor with value C and initial voltage as V0 that is stored across the capacitor, if you connect it to a resistor of value R, at any point of time the voltage across the capacitor, so this is now Vc of t or V of t is given by V0 into e power minus t by rc. So the expression for the voltage across the capacitor will be this. Suppose if you write the probable graph for this, so suppose if you are writing it as v of t, so you know that when t is equal to 0, suppose you substitute t is equal to 0 here, then this becomes v0. The initial voltage is v0 here. As time elapses, we know that this is keep on reducing, and it is reducing exponentially. And we also write one more term that is known as time constant. Time constant will be written as tau, that will be equal to the product of the resistor and the capacitor. So you can rewrite this expression v naught of v of t, that is voltage across the capacitor at any point of time, is given by v naught into e power minus t by tau. So this is the expression for the capacitor voltage at any point of time with a time constant Rc, where R and C are the values of the resistor and capacitor which are there under consideration. Suppose if you consider t is equal to tau, because we know that R into C happens to be in terms of second, that is if R is equal to 1 kilo ohm and C is equal to 1 microfarad, I will end up with Rc as equal to 1 millisecond. So if t is equal to 1 millisecond, suppose if you have V0 is equal to, suppose the value of V0 is around 10 volt, if the value of V0 is 10 volt and the values of R and C is equal to 1 kilo ohm and 1 microfarad, so at a time t is equal to 1 millisecond, suppose if you take this is equal to 1 millisecond, which is equal to tau, the corresponding voltage across the capacitor will be exactly equal to, suppose now if I substitute all these things here, so v at 1 millisecond, will be equal to 10 into e power minus t is equal to now 1 milli, tau is also 1 milli, so this is 1 milli by 1 milli, it is e power minus 1. This happens to be 10 into 0.368, that is 3.68 volt, meaning at this time t is equal to tau, which is equal to 1 millisecond. For this specific example, the voltage which was there at 10 volt reduces to 3.68 volt. 3.68 volt. Likewise, we can certainly find out what is the capacitor voltage that is there available across this capacitor as time elapses if it is connected to a resistor of value R. So this is the graphical representation of the dissipation of voltage, that is charges across the capacitor, and which results in a capacitor voltage V of t. If you can clearly note here that we don't have any source here, so this type of RC network analysis is a source free analysis because we don't have any voltage source connected to this circuit at all. What we assumed is there is a capacitor having an initial voltage of V0. So this is a RC network analysis without any source. This is source free RC network analysis, which ends up in having an expression for V of t is equal to V0 into e power minus t by tau, where tau happens to be the time constant of the network. So after understanding this particular expression for the capacitor voltage whenever it is connected to a resistor of value R, so let us take up this example and try to apply those equations and try to understand it better. So in this example, let us take the first example. We are being given, so there's a 12 ohm resistor and there is a 6 ohm resistor, and then we have a 8 ohm resistor connected here and have a capacitor of value 1 by 3 farad. So what is asked here is, so VC of 0 is given as 60 volt. We are asked to find out what is the voltage of capacitor with respect to time, that is VC of t, and we are asked to find what is Vx of t, where Vx is the voltage across this 6 ohm resistor. This is Vx, and then we are also asked to find what is the value of I0. of t. So the initial voltage across this capacitor is 60 volt. We are asked to find what is the VCT, that is voltage across the capacitor with respect to time, and what is the voltage across this 6 ohm resistor, and what is the current flowing through this 8 ohm resistor. So for this particular problem, so what we know is, we know this type of equivalent circuit, so we know what is this. So this is RC, and if I can able to bring the given circuit onto this form, then I can able to use the expression of VC of t is equal to V0 e power minus t by RC. So first and foremost thing is that we have to bring this particular circuit into this form, and then we can able to find out the value of R value, and of course the C value is that is already given, so we have to find out actually what is the value of R. So in order to bring the given circuit into the standard circuit, so we may have to consider, you can see these two are coming in parallel, so we have to find out the equivalent resistance of this, and then that is coming in series with this. Suppose if you find out what is the this you can reduce to a single resistor here, and then there is a 8 ohm resistor. This is actually, I think this comes out to be 12 into 6 by, so, and this becomes 18, and then we have this capacitor. Okay, this is 1 by 3, so this is okay. Now you can see this happens to be, I think this is 4 ohm. So, and then we will end up with this, because now these two will come in series, we will end up with a capacitor of 1 by 3 farad, and we have a resistor of 4 plus 8, 12 ohm. So this is now exactly in line with the expected circuit. So we have a capacitor of 1 by 3 farad, there's a resistance of 12 ohm. Now I can find out what is the value of tau, which is nothing but RC, which is equal to 12 into 1 by 3, which is now 4. So this is now the value of tau is actually 4 seconds. Now let us try to get the expression for Vc of t, which is nothing but V0. V0 is nothing but the initial voltage across the capacitor, which is now 60, and it is e power minus t by Rc. Rc is equal to actually 4. So this comes out to be 60 e power minus 0.25 t. So this is the expression for the capacitor voltage with respect to time. So it decays with this rate. It is e power minus 0.25 into t, because this 0.25 you are getting because this 0.25 is actually 1 over tau. 1 over tau. And then we are asked to find out what is Vx. Vx is nothing but the voltage that is there available across the resistor, 6 ohm resistor, out of the capacitor voltage here. Now I can just treat this as you have a capacitor voltage which is of Vc of t, and I have a resistor of 8 ohm, and I have an equivalent resistor of I think it is 4 ohm. So whatever voltage that comes across 6 ohm, the same voltage will be there across 12 ohm also. So instead of writing Vx as this, I can write this also as Vx, this also as Vx of t. So from this expression, from this circuit diagram, I can write Vx of t as equal to Vc of t multiplied by 4 ohm divided by the overall resistance. This is like a potential divider. Overall resistance is 8 plus 4, which is 12. So now I know what is this is. This is actually 60 e power minus 0.25 t into 4 divided by 12. So this is now 3. Now this comes out to be, so now Vx of t is equal to 20 e power minus 0.25 t. This is the expression for the voltage across this resistor of 6 ohm at any point of time. So if you want to find what is the value of the voltage across this capacitor at 2 seconds, you simply substitute t is equal to 2. If you want to find it at 1 millisecond, substitute the value of t as 1 milli. So we can able to get the expression, or we can able to get the exact value of the voltage across the resistor. And then we are asked to find what is the value of I0. What is the value of I0? So I0 is nothing but because I0 is the current that is flowing through 8 ohm resistor. Since this 8 ohm resistor is actually in series with this entire resistor of course this way happens to be 4 ohm. So now this is what is I0, and you can say this is I0, this is I0. So I can find out what is I0 of t. So from this circuit diagram, so whatever you have now is, so now this is 4 ohm and this is 8 ohm, and then you have a capacitor voltage which is with respect to time as Vc of t, and you're looking at current I of t or I naught of t. I can write I naught of t as equal to Vc of t divided by, that is voltage divided by the entire resistance. Resistance is actually 12 ohm, because because these two are in series, the resistance comes out to be 12. Then I can write it as it is 60 e power minus 0.25 t by 12, which happens to be now 5. So I naught of t is equal to 5 e power minus 0.25 t. So from this example, we can able to use the expression of V of t, that is voltage across capacitor t is given by V0 into e power minus t by RC. To find out the value of R, we actually found out the equivalent resistance, which was coming out to be 12 ohm, equivalent resistance of the entire network, which is the parallel combination of these 6 and 12 ohm resistor, that is 4 ohm, that is coming in series with this 8 ohm, which has become 12 ohm, and that 12 will be the value of R, and of course we have been given the value of C. So we end up with the expression for voltage across capacitor, voltage across this resistor, 6 ohm resistor, and the current through this entire 8 ohm resistor, which happens to be the overall current in the circuit. Okay, let us also try to work out a more problem where you have something like this type of circuit. So let me consider a voltage source which is now 24 volt is given, and I have a 6 ohm resistor, and I have a switch, and there is a capacitor of value 1/6 farad, and I have two resistors which are connected in parallel. One is 12 ohm, other is 4 ohm. So what is said now is this switch S is closed is closed at t equal to 0. At t equal to 0, this switch S is closed. This switch S is closed at t is equal to 0. We have been asked to find out what is Vc of t, that is voltage across the capacitor, and what is the uh, energy that is stored in this capacitor. So Vc of course 0. What is the energy that is stored in the capacitor? To know what is the Vc of t, so we know that because here also you can see, even though we have a source here, sorry, this is not, switch is not closed, it's actually opened. Switch is opened at t is equal to 0. So why it is opened is initially it is closed. So what will happen is at t is equal to 0 second, I just open it. So before I open, it is actually in closed mode. Whenever it is closed, out of 24 volts, some voltage will be get stored in this capacitor, and that will be your V0. Okay, Vc of 0. Vc of 0 is nothing but the initial voltage of this capacitor when this switch is closed. So when this switch is closed, we know that the equivalent circuit looks like this. So I can rewrite the equivalent circuit at t less than 0. At t less than 0, because at t equal to 0, I'm just opening the switch. So at t less than 0, switch is closed. Switch is closed. When the switch is closed, this is how the circuit is looking like. So I have a capacitor, and I have, of course, I'll write the equivalent resistance. Now this will be 3 ohm, so it is 6 ohm. So I have a 24 volt, and there is a capacitance of 1/6 farad. Now what is Vc0? Vc0 is nothing but the voltage across the capacitor before I open the switch. When the switch is closed, now this is a circuit how it looks like. So you can see out of 24 volt, because since it's a DC voltage, this capacitor looks like an open circuit for this DC. If you want to know what is the voltage across this, okay, V0 Vc of 0, I have to actually find out of this 24 how much is being dropping here. So we can actually find out what is Vc0, that is voltage across the capacitor when this switch is closed. It's actually 24 volt multiplied by 3 ohm divided by the overall resistance, which is 9. So if you solve for this, so this happens to be 3 and this is 8 volt. So the capacitor will initially hold a charge corresponding to voltage 8 volts, and of course we have a capacitance of 1/6 farad. So now we could able to know what is the initial voltage across the capacitor, which is equal to now 6 volts. So once we know what is the initial voltage, so we can find out what is Vt, that is voltage across the capacitor at any point of time when the switch is actually open. When I open the switch, how does the circuit will look like? The circuit will look like this. So it is now 24. This is now just a minute. This is now equal to 6 ohm. Now the switch is open. This is now 1/6 with 8 volt across it, and then you have a resistor of equivalent 3 ohm. Now what is this VCT? VC of t is nothing but V0 e power minus t by RC. Now we know the value of R, we know the value of C. So what is the value of R? The value of R is equal to 3 ohm. The value of C is equal to 1 over 6. So tau is equal to RC is equal to now is actually half. It's actually half. So if you want to know what is Vc of t, Vc of t is nothing but 8 e power minus t by half. So now this value of Vc, that is voltage across the capacitor at any point of time, is given by 8 e power minus 2t. So this is the expression for the capacitor voltage when the switch is open circuited. Because when the switch becomes open, so we will end up with there is a capacitor voltage, initial voltage of 6 volt will be start dissipating across resistor with this expression. Of course we can find the value of energy, that is charge that is stored in this capacitor, which is now given by Vc of 0 is given by the expression. Let me just write it. So I have a equivalent. Vc of 0 is nothing but half Cv square. I know the value of C as 1 over 6 farad. I know the value of V, which is equal to 8 volt. So naturally, because we are looking at T is equal to of course just before the opening of this switch, okay, what is the charge that is stored in this capacitor, that is energy stored in this capacitor? It is now half into 1 over 6 multiplied by, so it is now 64. You end up with, so this is now 2, so now you end up with 32. It is 32 by 6, happens to be 5.33 joules of energy stored. So this is the value of the energy that is stored in the capacitor before I open the switch. Okay, once I open the switch, it will start dissipating across. Okay, because of this, resistor is coming in parallel with this. So this way we can able to use the expression that we derived in this particular video, which is a capacitor will certainly discharge. Suppose if this is R, this is the value of C, and this is V0 is the voltage across the capacitor initial charge. And if you want to know what is the capacitor voltage at any point of time, we know that if this is V0, depending on the time constant, because V of t is given by V0 e power minus t by RC. Of course this can also be written as V0 e power minus t by tau. If tau is too large, it decays slowly. If tau is slightly larger, of course it decays a bit fast. If tau is very small, then it decays quickly. You can see it decays very quickly. So this is how, of course, this discharge of this capacitor voltage purely depends on the value of tau. It is actually inversely proportional. If the value of tau is less, it discharges quickly. So when the value of tau will be less, if the value of RC time constant is less, then it discharges very quickly. Okay, this way we can able to understand the working of this RC network in the absence of a source. So there is no source existing, but still we are assuming there is a voltage of V0 being stored across the capacitor before I connect a resistor to the capacitor so that it starts discharging.